NCRT podcast by me, Anoop Vashisht. Organic chemistry, some basic principles and techniques. Unit 12, Organic chemistry, some basic principles and techniques, chemistry part 2, NCRT podcast. Objectives. After studying this unit, you will be able to understand reasons for tetravalence of carbon and shapes of organic molecules. Write structures of organic molecules in various ways. Classify the organic compounds. Name the compounds according to IUPAC system of nomenclature and also derive their structure from the given names. Understand the concept of organic reaction mechanism. Explain the influence of electronic displacement on structure and reactivity of organic compounds. Recognize the types of organic reactions. Learn the techniques of purification of organic compounds. Write the chemical reactions involved in the qualitative analysis of organic compounds. Understand the principles involved in quantitative analysis of organic compounds. In the previous unit, you have learned that the element carbon has a unique property called catenation, due to which it forms covalent bonds with other carbon atoms. It also forms covalent bonds with atoms of other elements like hydrogen, oxygen, nitrogen, sulfur, phosphorus, and halogens. The resulting compounds are studied under a separate branch of chemistry called organic chemistry. This unit incorporates some basic principles and techniques of analysis required for understanding the formation and properties of organic compounds. General introduction. Organic compounds are vital for sustaining life on Earth and include complex molecules like genetic information bearing deoxyribonucleic acid, DNA, and proteins that constitute essential compounds of our blood, muscles, and skin. Organic compounds appear in materials like clothing, fuels, polymers, dyes, and medicines. These are some of the important areas of application of these compounds. Science of organic chemistry is about 200 years old. Around the year 1780, chemists began to distinguish between organic compounds obtained from plants and animals and inorganic compounds prepared from mineral sources. Berzelius, a Swedish chemist, proposed that a vital force was responsible for the formation of organic compounds. However, this notion was rejected in 1828 when F. Wohler synthesized an organic compound, urea, from an inorganic compound, ammonium cyanate. The pioneering synthesis of acetic acid by Kolb 1845 and that of methane by Barthelot 1856 showed conclusively that organic compounds could be synthesized from inorganic sources in a laboratory. The development of electronic theory of covalent bonding ushered organic chemistry into its modern shape. Tetravalence of carbon. Shapes of organic compounds. The shapes of carbon compounds. The knowledge of fundamental concepts of molecular structure helps in understanding and predicting the properties of organic compounds. You have already learned theories of valency and molecular structure in Unit 4. Also, you already know that tetravalence of carbon and the formation of covalent bonds by it are explained in terms of its electronic configuration and the hybridization of s and p orbitals. It may be recalled that formation and the shapes of molecules like methane CH4, ethene C2H4, ethine C2H2 are explained in terms of the use of sp3, sp2 and sp hybrid orbitals by carbon atoms in the respective molecules. Hybridization influences the bond length and bond enthalpy, strength in compounds. The sp hybrid orbital contains more s character and hence it is closer to its nucleus and forms shorter and stronger bonds than the sp3 hybrid orbital. The sp2 hybrid orbital is intermediate in s character between sp and sp3 and hence the length and enthalpy of the bond it forms are also intermediate between them. The change in hybridization affects the electronegativity of carbon. The greater the s character of the hybrid orbitals, the greater is the electronegativity. Thus, a carbon atom having an sp hybrid orbital with 50% s character is more electronegative than that possessing sp2 or sp3 hybridized orbitals. This relative electronegativity is reflected in several physical and chemical properties of the molecules concerned, about which you will learn in later units. Some characteristic features of pi bonds. In a pi bond formation, parallel orientation of two p orbitals on adjacent atoms is necessary for proper sideways overlap. Thus, in CH2-CH2 molecule, all the atoms must be in the same plane. The p orbitals are mutually parallel and both the p orbitals are perpendicular to the plane of the molecule. Rotation of one CH2 fragment with respect to other interference with maximum overlap of p orbitals, and therefore such rotation about carbon-carbon double bond C double bond C is restricted. The electron charge cloud of the pi bond is located above and below the plane of the bonding atoms. This results in the electrons being easily available to the attacking reagents. In general, pi bonds provide the most reactive centers in the molecules containing multiple bonds. Problem 12.1. How many sigma and pi bonds are present in each of the following molecules? A. HC triple bond C CH double bond CH CH3. B. CH2 double bond C double bond CH CH3. Solution. A. Sigma C single bond C 4, sigma CH 6, pi C double bond C 1, pi C triple bond C 2. Sigma C C 3, sigma CH 6, pi C double bond C 2. Problem 12.2. What is the type of hybridization of each carbon in the following compounds? CH3Cl, B. CH3 twice CO, CH3Cn, HCONH2, CH3CH double bond CHCN. Solution. sp3, B. sp3sp2, C. sp3, D. sp2 sp3 sp2 sp2 sp. Problem 12.3. Write the state of carbon in the following compounds and shape of each of the molecules. H2C double bond O, B. CH3F, C. HC triple bond N. Solution. A. sp2 hybridized carbon, trigonal planar. B. sp3 hybridized carbon, tetrahedral. C. sp hybridized carbon, linear. Structural representation of organic compounds. Complete, condensed, and bond-line structural formulas. Structures of organic compounds are represented in several ways. The Lewis structure or dot structure, dash structure, condensed structure, and the bond-line structural formulae are some of the specific types. The Lewis structures, however, can be simplified by representing the two electron covalent bond by a dash. Such a structural formula focuses on the electrons involved in bond formation. A single dash represents a single bond. Double dash is used for double bond and a triple dash represents triple bond. Lone pairs of electrons on heteroatoms, example oxygen, nitrogen, sulfur, halogen, etc., may or may not be shown. Thus, ethane C2H6, ethene C2H4, ethyne C2H2, and methanol CH3OH can be represented by the following structural formulas. Such structural representation are called complete structural formulas. These structural formulas can be further abbreviated by omitting some or all of the dashes representing covalent bonds and by indicating the number of identical groups attached to an atom by a subscript. The resulting expression of the compound is called a condensed structural formula. Thus, ethane, ethene, ethyne and methanol can be written as CH3CH3, ethane, H2C double bond CH2, ethene, HC triple bond CH, ethyne, CH3OH, methanol. Similarly, CH3, CH2, 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 CH3 can be further condensed to CH3, CH2 whole 6 CH3. For further simplification, organic chemists use another way of representing the structures in which only lines are used. In this bond line structural representation of organic compounds, carbon and hydrogen atoms are not shown and the lines representing carbon-carbon bonds are drawn in a zigzag fashion. The only atoms specifically written are oxygen, chlorine, nitrogen, etc. The terminals denote methyl CH3 groups unless indicated otherwise by a functional group, while the line junctions denote carbon atoms bonded to appropriate number of hydrogens required to satisfy the valency of carbon atoms. Some of the examples are represented as follows. 3-methyl octane can be represented in various forms as CH3, CH2, CH, CH2, 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 CH3, नीचे CH3. Various ways of representing 2-bromobutane are CH3CHBr CH2CH3. In cyclic compounds, the bond line formula may be given as follows. Cyclopropane, cyclopentane, chlorocyclohexane. Problem 12.4. Expand each of the following condensed formulae to their complete structural formulas. CH3CH2CO CH2CH3, CH3CH double bond CH CH2 whole thrice CH3. Solution. Problem 12.5. For each of the following compounds, write a condensed formula and also their bond line formula. HOCH2 CH2 CH2 CH CH3 CH CH3 CH3. Solution. Condensed formula HO CH2 whole thrice CH CH3 CH CH3 whole twice, HO CN CN whole twice. Bond line formula. Problem 12.6. Expand each of the following bond line formulas to show all the atoms including carbon and hydrogen. Solution.